Hi everyone, hope you are all doing okay. Today in this lecture we are talking about shape functions. In FEM, solutions or values of field variables are available only at nodal points. Shape functions helps to approximate the effect of the field variables in other points within the elements by the interpolation of nodal variables. So basically we are talking about an interpolation function. So consider a three-noded triangular element. We are considering 2D elements here. In this element, the nodal points are represented by this green arrow. So all the three vertices of the triangle are nodal points whose value has been calculated by using FEM. And if you look into the points inside the triangle, we don't know its value. So we use shape functions to find those values. The nodes are exterior. At any point within the element, the field variables are described by the equation given below. Phi of xy is equal to n1 of xy phi1 plus n2 of xy phi2 plus n3 of xy phi3. So here in this equation, phi1, phi2, phi3 are the values of field variables. Means they can be the value of the particular physical quantity like displacement in the nodal points that you have calculated. n1, n2, n3 are the respective interpolation functions or shape functions. So let's talk more about shape functions. The interpolation functions n1, n2, n3 are also called shape functions. Sometimes they may be used to express the geometry and shape of the element. Shape function has unit value at nodal point and zero value at the other nodal point. That's obvious, right? Because we know that interpolation function starts from 0 or from a small value or a particular value and then goes on increasing or decreasing and then reach a maximum value or minimum value. So like that, shape function has also follows that. So in one-dimensional problems, the basic field variable is displacement. So let us consider, let u be the displacement at any point on an element. Then capital U is equal to sigma ni ui, where ui is the displacement of the ith node and n is the shape function of the ith node. So we can write u is equal to n1 u1 plus n2 u2 plus n3 u3. Similarly, if we consider the displacement in y direction as v is equal to sigma ni vi, where and also on expanding v is equal to n1 v1 plus n2 v2 plus n3 v3, where n1 and n2 n3 are respectively shape functions of the node points that we have calculated 1, 2 and 3, and v1, v2, v3 are the displacements. In general, shape functions should satisfy the following. First derivative should be finite within the element. This is because if the derivative is not finite, it may be infinity, then there will be sudden change in the geometry of the shape function and we don't want that. So and also displacement should be continuous across the element boundary. Characters of shape functions. Shape functions has unit value at its nodal point and zero value at other nodal points. We have discussed that it's an interpolation function. It does that. So and also some of the shape functions are equal to 1. If you can, let's talk about polynomial shape functions. When we are finding an interpolation function or shape function, we have a lot of options. We could go for logarithmic functions, we could go for trigonometric functions, we could go for exponential functions, etc. But why we go for polynomial functions? Because polynomial functions, in polynomial functions, differentiation and integration of polynomials are very easy. It is easy to formulate and computerize the finite element equations, and most importantly, the accuracy of the result can be improved by increasing the order of the polynomial. Last point tells us that the polynomial shape functions gives us a flexibility. We can select the error in our calculations. By increasing the order of the polynomial, we can fit or find a better curve that can represent our node or element. So that gives a sort of lot of power. So that's one of the most important points why we choose a polynomial shape function. Now, approximation of nonlinear one-dimensional function by using polynomials of different order. Here we have three different figures. Let the first curve represents the movement pattern for the non-nodal point. In other words, this curve represents the profile of non-nodal movement. To find displacement in other points, we need to formulate shape functions. In order to develop that shape function, we need to select a suitable polynomial which can represent the profile of movements of non-nodal values. Here, in the first figure, since the polynomial selected for the formulation of shape function, there is only one common point between the actual curve and the curve generated based on shape function. In second figure, however, two points are common but not matching with the actual profile, so it's of no good either. But in case of the third figure, as the polynomial selected for the formulation of shape function is almost correct, the geometry of two curves are nearly same. From that, we can infer that a suitable polynomial is to be selected for the formulation of shape function. In order to optimize the correct terms and the order of the polynomial, we are mainly selecting the polynomial based in various levels in a Pascal's triangle, which we will be discussing in the following slides. So, case 1, linear polynomial as displacement field variable. For one dimensional, we can write an interpolation of shape function as u of x is equal to a0 plus a1x. For two dimensional, u of xy is equal to a0 plus a1x plus a2y, and for three dimensional objects, u of xyz is equal to a0 plus a1x plus a2y plus a3z. So, case 2, quadratic polynomial as a displacement field variable. For one dimensional, in case of quadratic polynomials, u of x is equal to a0 plus a1x plus a2x square. For two dimensional, u of xy is equal to a0 plus a1x plus a2y plus a3x square plus a4y square plus a5xy. For three dimensional, u of xyz is equal to a0 plus a1x plus a2y plus a3z plus a4x square plus a5y square plus a6z square plus a7xy plus a8yz plus a9xz. So, as we can see from these equations, we have calculated or formulated these equations via using the Pascal's triangle. There are a lot of advantages when we formulate these equations from the Pascal's triangle, which includes advantages like symmetry, convergence, etc., which are very important in FEM. But however, we will not be talking about them. You can refer them or study more about them in other FEM tests. So hope you are all doing okay and be safe. Thank you.